Okay, picking up with lesson 2, we're going to pick up where we left off, and that is the wave mechanical model, which is the modern view of our atom currently. And that is a combination of Schrodinger and de Broglie, worked on a wave mechanical model of the atom, and the electron is visualized as a standing wave, opposite of like a traveling wave, and so it's not like in discrete planetary orbits around the nucleus. There are areas of probability of where that electron is located. This should ring a bell. Shapes of these orbitals, the wave function, which is that funny looking trident sign of the Schrodinger equation, which don't worry, you will not have to calculate. But it tells us the function of the x, y, and z coordinates of the electron's location in space. So here is your S, your P, your D, and your F. We'll go into those more in a little bit, but that's what they would look like around the nucleus if they were rotating around. That brings us to Heisenberg uncertainty principle. In a nutshell, it basically says we cannot know both the position and the velocity of a particle at any given time. And so the accepted definition of the size of a hydrogen 1s orbital is that the radius of the sphere encloses the 90% of probability of where that electron is located. So when we're talking about this means we're 90% sure of that's where the electron is located. So that's going to take us into electron configuration, which I hope that you remember from last year, because we're going to go through it pretty fast and furious here. So electron arrangement, of course, is the way the electrons are arranged in their series of levels and sublevels, or shells and subshells. So we start with energy level 1, and then 2, 3, etc., etc. Currently we have 7 energy levels, but in theory we could have up to infinity if they keep making atoms. Creating them in the lab with higher and higher and higher atomic numbers, and of course we're going to need higher and higher energy levels. I do believe in your lifetime you will see an 8th period or an 8th energy level added to the periodic table, because they are currently working on synthesizing element 119, which does not fit in period 7, so they would have to create a new period for the periodic table. And of course, the further away it is, larger the orbital, higher energy, further away from the nucleus. Okay? So here are our energy sublevels. We've got S, P, D, and F. That is the order that they fill. I always remember it with science. It's pretty darn fun. Of course, the S orbital, or S sublevel, has 1 orbital, holds 2 electrons. We call it a spherical shape. The P sublevel has 3 orbitals, holds 6 electrons. Each orbital holds 2 electrons. Okay, so each one of these shapes that we're showing around the XYZ axis is able to hold 2 electrons. The D holds 5 orbitals for a total of 10 electrons, and the F holds 7 orbitals for a total of 14 electrons. Quantum numbers, we did that in pre-AP Chem, if you were in there with me. And quantum numbers basically give you the address of the electron. Guess what? Don't worry, you do not actually have to do quantum numbers in AP Chem, because it is no longer tested on the AP exam, so we won't go over them. But we did do them in pre-AP because I feel like they're important to help you understand the location of the electron. But you do need to understand not only the arrangement, but what some of these are. The first one is the principal quantum number, which is basically telling me your energy level. The angular momentum quantum number is saying, hey, I'm in an S, a P, or D, and F, and those are the numbers that go along with those. S is 0, P is 1, D is 2, F is 3. The magnetic quantum number is basically say, hey, which one of those orientations was I in? And the values are negative L to positive L. So I'll give you an example of that and see if it rings a bell. Let's say I'm in a P, and the L value for a P is 1. So that means 1, 2, 3 orbitals in a P orbital or a P sublevel. And so I would say negative 1, 0, and positive 1. And depending on where that electron was placed, in whichever one, that would be the number that I would ascribe to it. So let's say it was a P2, it would go 1, 2, and so the second number would be this right here, 0. Okay? And then the spin number is clockwise or counterclockwise, so if spinning up, is a half, and spinning down is a negative half. But again, we're not tested over those, but I wanted to just show you that. Orbital shapes and energies. Of course, the orbitals have the regions of probability up to 90%, and then there's regions of 0 electron probability, and we call those area nodes. And so in here, this drawing, this would be these white spaces in here. Whoops, sorry. It would be, these white spaces would be the nodes. We're not going to find it there, or in this case here or here. So those would be where you would not find the electrons. Degenerate orbitals, or orbitals that are all in equal energy. So basically it's your P has 3, so they're all equal energy. D has 5, all equal energy. S have 7, all equal energy with each other. Pauli exclusion principle. Now we're into the 3 rules that govern how we do electron configuration. Pauli exclusion principle states that in a given atom, no 2 electrons can have the same set of 4 quantum numbers. An orbital can only hold 2 electrons, and they must have opposite spin. So we spin one up, spin one down, hence the graphic with Pauli's name. Aufbau principle is the principle that states that electrons will enter the orbitals of the lowest energy first. In the ground state, atoms always will have their electrons in the lowest energy orbitals. Here is the order that fills. And here's a graphic of you seeing the energy. Also, this is also showing how these, and these are all degenerate in terms of the 4Fs are all equal to each other in energy level. But if you look at this, you'll notice that 4F doesn't even show up until like after 6S. Yeah, 6S is a little bit lower. And so they don't even show up till then. This is the order that they fill. You do not have to memorize this because we're going to do this based on the periodic table. Hopefully you remember from last year, but we will do it again real quick. And then the third one is Hund's Rule, and it states that when you're filling an orbital within a sub-level, that they must be half filled with electrons before having a second electron, which is spinning down. Okay? In other words, everybody gets one up arrow before they get a down arrow. That's basically what it's saying. This is what I was talking about. We don't have to memorize the order that they gave us on the previous slide, and I've given you a copy of this chart that you can refer to. And the periodic table is arranged the way it is based on its electron configuration, and if it's in the S block, it means the last electron is going into either the S, this case it would be the S1, the last electron. If it was going the second, it would be in this one, an S2. And then we'd skip over to the P. Go ahead and write that. That's, whoops, what happened there? Sorry about that. I got too close to the edge. So this would, we said this one was S1, this one was S2, P1, P2, etc. And then D1 over to D10. And then this is F1 over to F14. And so remember, we start here and we read at the top. Sorry, I keep getting close to the edge. Exceptions to the Aufbau principle. The good news is you're not responsible for them on the AP exam. You were in Chem 1, so that when you saw it, you'd know. But I do want to explain to you that some elements have an exceptional electron configuration. For instance, for copper, we would expect that that would end based on the filling of 4s1 and 4s2, 3d9, but instead it actually is going with this one right here because it's more stable, because it is fewer electrons sharing orbitals, and so it minimizes the repulsion. But basically, if you see one that doesn't look like it should, it's most likely it's an exception. There are 3 types of ways that we can depict orbital notation, and so the first way is the orbital notation or orbital diagrams. We're going to draw arrows or boxes. We usually will do lines and boxes. So I would have drawn this as 1s up and down, and I draw half arrows just because they're faster. 2s up and down, 2p up, up, up. Okay? And so that's the way we do those, is drawing the arrows. And then, of course, just standard electron configuration is when we would basically take what we just had, which was up, up for 1s, up, up for 2s, and then 2p was 1, 2, 3. So we're literally just saying, hey, then 1s2, 2s2, 2p3. We're literally just saying what was in those orbitals we drew. And then the last one is noble gas notation, and that is where we use the previous noble gas and then just say what comes after it. And so here's an example of that. So if I was going to do phosphorus, I look and see where phosphorus is. It comes after neon. So anything that comes after neon is going to have at least this basic notation in it. So we say neon, and then whatever comes after that, 3s2, 3p3. Okay. Now, let's just look at that real quick. Periodic table. So you just look at what noble gas comes before. For instance, if I was trying to do noble gas configuration for copper, which is element number 29, I would use argon as my noble gas. If I was doing it for, say, silver, then I would use krypton as my noble gas, and then gold, I would use xenon. If I'm doing the noble gas notation of another noble gas, I do not just use its own symbol in brackets. For instance, for argon, I wouldn't just write the noble gas configuration of argon as argon. I would say neon in brackets, 3s2, 3p6. Okay, so we're going to practice that. If we're talking about ions in electron configuration, remember charged particles. If it's negative, it means it gained some electrons. If it's positive, it means I took away some electrons. So just take that many electrons out when you're doing the noble gas configuration. All right, let's practice these two, and then we're going to call this lesson done. Write the electron configuration for copper. So what I like to do is I like to find out where is it at in the thing, and see what it ends in, and I just do it until then. And because you are not responsible for the noble gas configuration, unless they gave you it and asked you why, you would not do the exception. You just go ahead and do it how we're supposed to. But we're going to start with carbon down here first because, well, quite frankly, it's easier. So we're going to start with carbon. Carbon has 6 electrons. And if I look at where it's located on the table, I see that it's going to end in 2p2. So I'm going to start, and I'm going to say 1s2, 2s2, 2p2. If I was going to do argon, I would say argon has 18 electrons. It ends in 3p6. So I'm going to start at the beginning and say 1s2, 2s2. After that comes 2p, and I fill those up, 2p6. Then 3s2, and then 3p6. Okay. Now we'll go back and do cobalt, because we're going to have to use some D's in there. So if you notice when you're looking at the chart that I gave you, when you're in the S and the P block, you are in the same period number as what you're in. 1s is in the first period, 2s is in the second period, 3s is in the third period, etc., etc. When you get to the D block in the middle, you'll notice that you're always 1 less in the period number. And that is because it takes less energy, or it's a lower energy level to fill 4s than it is to fill 3D. So this part gets a little confusing because we're going to fill up the 4s. So like we're looking at cobalt, which is element number 27, we're going to fill up the 4s, and then we're going to go back and fill in the 3D, okay? Which is the order that it fills. But it's the opposite when you start taking electrons out. When you start taking electrons out to form bonds, it's actually going to come out of the 4s because there's 2 in there, and they are technically in a higher energy level, which is different than the amount of energy to fill the orbital, so that gets a little bit confusing, okay? So we're going to do cobalt, which has 27 electrons. And if I look at that, it's 3D. Let's count over. 1, 2, 3, 4, 5, 6, 7. So it's going to end in 3D7. So I'm going to start at the beginning, and I'm going to say 1s, I fill them up. 2s is next, I fill it up. Go across to the next side, 2p6, I fill it up. I go to the next period, 3s2, 3p6, then I fill 4s2, and then I'm going to do 3d7. Now, something that I didn't make you do in pre-AP Chem is I would let you leave it like that, but many times you'll see it in AP. They're going to rewrite that, and they're going to put it in the order that it actually comes at. So 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. So they will rewrite it and keep all of the energy levels or principal quantum numbers together. So you've not been used to seeing that, so that's something that we're going to have to start doing. If you are realizing that I don't really remember how to do electron configuration and she's going really, really fast, it will be up to you to go find you a tutorial video or come into tutorials to ask me some questions. I go over this really fast because it's fairly easy, and if most kids remember it, but if you don't, you're going to have to take some time to do that for yourself. Okay? All right. So we've done a couple of those. We'll do one more. Nah, we don't need to. It's pretty easy, right? Hopefully. If not, I guess I'll be seeing you for tutorials. And then we're going to do some noble gas configurations on the next slide. All right, so write the electronic configuration for noble gas, okay? So we're going to do the noble gas. And these are giving us some ions, so we're going to do two birds, one stone, so to speak. So fluorine normally has 9 electrons, but because of this negative, we're going to say we're adding an extra electron. So we're going to do 10 electrons. Okay? So the noble gas that comes before fluorine, well, it's helium. So technically I could do helium for that. But honestly, most people don't. Most people just say, because the difference between writing helium and 1s2 is not that big a difference. So it's going to be 1s2, 2s2, 2p6. Normally it would end in 2p5, but we added an electron. If I look at calcium, the noble gas I'm going to use for calcium is going to be argon. Okay? Normally calcium has 20 electrons, but because of this 2+, that means we took off. So we're going to say 18 electrons. Well, guess what? Its noble gas configuration would actually be just argon. Okay? That would be it would have the same configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6. Okay? Sulfur 2-, guess what? Normally it has 16, but because we added 2, it also has 18 electrons. So again, it's going to have the same electron configuration as argon, or as this. Sodium plus means I gave away an electron, so I only have 10 electrons. It's going to have the same as neon, which is the same as this right here, 1s2, 2s2, 2p6. And then aluminum is 3+, so aluminum normally has 13, but it's going to drop down to 10 electrons, which, guess what? Same configuration as neon, which is 1s2, 2s2, 2p6. These things, and we'll see this again, are said to be isoelectronic. Oops, can't spell. Helps put the glasses on. And what being isoelectronic means is they have the same outer electron configuration. Doesn't mean that they become neon. Aluminum ion is not becoming neon because it still has 13 protons in its nucleus. It's just an aluminum ion. Okay? And believe that's where we're going to stop. It is. Okay. All right. Signing off.